December 17th, 1944, 06:30 hours, 3 kilometers southeast of Malm, Belgium. SS Obersturmbannfuhrer Otto Skorzeny crouched behind a stone wall, watching the pre-dawn sky. His Panzer Brigade 150 had been attacking American positions for 18 hours. The advance had stalled. Something was wrong with the American artillery. The shells were detonating in midair, not hitting the ground, not burying themselves in the frozen earth before exploding, just bursting overhead, 30, 40, 50 feet above his men, showering shrapnel straight down. There was no cover. Foxholes offered no protection. Men died in trenches that should have kept them safe. Communication wires snapped from fragments that fell like steel rain. Skorzeny had commanded special operations since 1940. France, the Balkans, the rescue of Mussolini. He knew artillery, every type, German, Soviet, American. He understood how timed fuses worked. Gunners calculated distance and velocity, set the fuse. The shell exploded at a predetermined time after firing. Skilled crews could achieve airbursts, but it required perfect calculations, forward observers with clear sight lines, constant adjustments, and the weather was terrible. Heavy clouds, snow, zero visibility. The Americans should not be able to achieve accurate timed airbursts under these conditions. Yet here they were. Shell after shell exploding precisely overhead. No craters, no wasted explosions in empty ground, just perfect airbursts, every single time, regardless of terrain, regardless of visibility, regardless of weather. His officers reported casualties mounting, not from direct hits, from fragments. Men wounded in the back, the top of the head, the shoulders. Wounds that came from above. The Panzer crews were terrified. Inside their tanks they were safe from small arms fire, relatively protected from artillery impacts. But these airbursts sent shrapnel down through the thin roof armor. Drivers reported hearing explosions directly overhead, then the sound of metal striking metal, fragments punching through hatches, killing commanders, wounding loaders. The psychological effect was devastating. German soldiers had learned to survive artillery bombardment. Dig in, wait for the barrage to end, move during the gaps between salvos. But there was no surviving this. The shells found you wherever you hid. If you were in a trench, the explosion overhead sent fragments straight down into your position. If you were behind a wall, shrapnel rained from the sky at angles walls could not block. If you were in a building, the fragments came through the roof. One of Skorzeny's battalion commanders radioed. The men were refusing to advance, not cowardice. They simply could not understand how to survive. Soldiers need to believe their training and tactics work. They need to think they can avoid death through skill and caution. But skill meant nothing against artillery that exploded, precisely overhead every time. Caution provided no advantage when fragments fell from the sky regardless of where you positioned yourself. The only option was to stay buttoned up inside vehicles or remain in reinforced concrete positions. Neither allowed offensive operations. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Skorzeny ordered a tactical withdrawal. Pull back 500 meters. Regroup. Assess. His forces disengaged and moved to secondary positions. The American artillery followed them. More airbursts, more precise detonations. No matter where his units repositioned, the shells found them and exploded overhead. By 0800 hours, Skorzeny's attack had completely stalled. His brigade had suffered 200 casualties, not from American counterattacks, not from close combat, from artillery alone. Artillery that detonated with impossible precision and under impossible conditions, using a method his experienced officers could not explain. The Battle of the Bulge had begun 30 hours earlier on December 16th, 1944, at 05:30, Hitler's last major offensive in the West. Operation Watch on the Rhine. 250,000 German troops, 1,400 tanks and assault guns, 2,600 artillery pieces. The objective was Antwerp. drive west through the Ardennes forest, cross the Meuse River, capture the port, split the Allied armies, force negotiations, change the course of the war. The plan depended on speed, surprise, and weather. Speed to reach objectives before American reinforcements arrived. Surprise to overwhelm thin American lines in the Ardennes. Weather to ground Allied aircraft and neutralize American air superiority. The Germans achieved all three conditions. American units in the Ardennes were surprised, outnumbered, and scattered. Heavy snow and cloud cover grounded the Allied air forces. Roads jammed with American vehicles retreating in disorder. German spearheads advanced rapidly through gaps in the American lines. Everything was proceeding according to Hitler's plan, except the artillery. American artillery battalions, even those cut off and surrounded, continued firing with devastating effectiveness, and the shells were exploding in ways German soldiers had never encountered. The phenomenon was not limited to Skorzeny's sector. Reports came in from all along the German front: 1st SS Panzer Division, 5th Panzer Army, 6th SS Panzer Army. Every unit reported the same thing: American artillery shells exploding overhead, perfectly timed airbursts, casualties mounting, no way to take cover, no way to advance under the bombardment. At first, German intelligence officers assumed the Americans had developed improved forward observation techniques. Perhaps new radio equipment allowed precise fire control even in poor visibility, but that explanation did not account for the consistency. Every shell, every time, in every sector, perfect airbursts regardless of weather, terrain, or tactical situation. Something else was happening, some new technology the Germans did not understand. Colonel Georg Axelson commanded the United States 406th Artillery Group. His headquarters sat in a farmhouse near Monschau, Germany, on the northern shoulder of the German offensive. He had received the new ammunition 2 days earlier. Wooden crates marked POSIT, top secret. Handle with extreme care. Do not allow to fall into enemy hands. Destroy all duds immediately. The instructions were explicit. These shells contained a new type of fuse. Radio proximity fuse. Variable time fuse. VT for short. The fuse did not require manual time setting. It sensed the ground and detonated automatically at the optimum height for maximum fragment dispersion, approximately 20 to 50 feet above the target. The technology was classified higher than radar. Development had cost more than $1 billion. More than 3% of all physicists in the United States had worked on the project at some point. The Pentagon had forbidden use over land for nearly 2 years, fearing a dud might fall into German hands. German engineers might reverse engineer the device, develop their own version, use it against Allied bombers. The consequences would be catastrophic. American and British heavy bombers relied on altitude and formation flying for protection. German anti-aircraft artillery already inflicted heavy casualties. It took approximately 4,000 rounds of traditional flak, costing 100 marks each, to down a single bomber. With proximity fuses, that number would drop dramatically, perhaps 10 to 1, perhaps 5 to 1. The bomber offensive might become unsustainable, but General Dwight Eisenhower had demanded authorization. The German offensive was breaking through. American units were surrounded. Artillery was the only support available until reinforcements arrived. On December 19th, 3 days into the offensive, all restrictions were lifted. 200,000 shells with VT fuses were shipped to artillery units across the European theatre. Code name POSIT. Axelson had tested the new ammunition on December 16th, the first day of the German attack. The 38th Cavalry Squadron was dug in near Monschau. German forces hit them hard. Infantry, armour, artillery preparation. The cavalry called for fire support. Axelson ordered his batteries to load POSIT rounds. The effect was immediate. German infantry formations, advancing across open ground, were caught in devastating airbursts. Fragments rained down from precisely 30 feet up. There was no cover. Trenches were death traps. Shell craters offered no protection. Men advancing in the open were scythed down. The German attack faltered. Units that should have overrun the cavalry position within an hour were stopped cold. Casualties mounted until the German commanders pulled back. Axelson watched through binoculars. He had commanded artillery since North Africa, Anzio, Normandy. He understood fire support. Traditional artillery was effective but inefficient. Impact fuses required direct hits. Timed fuses required skilled crews, good observation, constant adjustment. Most shells exploded harmlessly, buried in the ground, detonating too high, bursting too early or too late. Artillery battalions calculated effectiveness in rounds per casualty, typically hundreds of shells to achieve one kill, sometimes thousands. The math was brutal but necessary. Artillery consumed enormous quantities of ammunition to suppress enemy positions. But these new proximity fuses changed everything. Nearly every shell became lethal. The fuse sensed the ground using miniature radar. When the shell reached the optimum height, the fuse detonated automatically. No manual setting required. No forward observers needed. No calculations. Just point the gun. Fire. The shell would explode at exactly the right height to maximize fragment coverage. A single 105mm shell with a proximity fuse had a lethal fragment area of 3,000 square feet. Traditional time fuses? 60 square feet. 50 times more effective per round. For 155mm howitzers, the burst height averaged 30 feet. For 240mm howitzers, the optimum height was over 70 feet. The larger the shell, the higher the optimum burst to spread fragments over a wider area. The technology was simple in principle. The fuse contained a miniature radio transmitter and receiver, no bigger than a milk bottle. The transmitter sent out radio waves. The waves bounced off the ground. The receiver detected the reflected signal. When the signal reached a certain strength, indicating the shell was at the correct height, an electrical circuit closed. A small charge fired. The main explosive detonated. The shell burst. Fragments spread in all directions with maximum coverage. The principle was simple. The engineering was extraordinary. Consider what the fuse had to survive. Firing a 105mm shell generated acceleration forces of 20,000 times gravity. Instantly, the projectile went from 0 to 800 meters per second in milliseconds. The shock would destroy any normal electronic device. Then the shell spun. Rifling grooves in the gun barrel imparted rotation for stability. 25,000 revolutions per minute. Centrifugal forces that would shatter normal vacuum tubes. The fuse had to withstand all of that. Then function perfectly. In temperatures ranging from -50 degrees to +100 degrees. In rain, snow, humidity, after months in storage, after being transported thousands of miles. The development had required breakthroughs in multiple fields. Miniature vacuum tubes rugged enough to survive, 20,000 Gs. Batteries that could activate under extreme acceleration. Circuits simple enough to manufacture by the millions. Safety mechanisms to prevent premature detonation. Self-destruct features to ensure duds did not fall into enemy hands intact. The first successful test occurred in August 1942. The cruiser USS Cleveland fired proximity-fused ammunition against radio-controlled drone aircraft over Chesapeake Bay. The test was scheduled for 2 days. It ended on the first day. All the drones were destroyed. 4 bursts. 3 drones down. The Navy immediately ordered mass production. 5 companies. Crosley, RCA, Eastman Kodak, General Electric, McQuay Norris. Production started slowly, 500 units per day in late 1942. By late 1943, 40,000 units daily. By war's end, 70,000 units per day. Over 22 million fuses produced total. The first combat use was January 5, 1943. The cruiser USS Helena, operating off Guadalcanal, came under attack by 4 Japanese Aichi D-3A dive bombers. Helena's anti-aircraft guns fired proximity-fused 5-inch shells, 2 salvos. One valve destroyed without a direct hit. The shell exploded near the aircraft. Shrapnel did the rest. The Japanese never understood what happened. Their pilots reported ships with impossibly accurate anti-aircraft fire. The effect on Japanese tactics was profound. By 1944, some analysts suggested proximity fuses forced Japan to adopt kamikaze attacks. If you could not survive long enough to line up a conventional bombing run, you had only one option: crash directly into the target before the proximity-fused shells killed you. Statistics confirmed the effectiveness. In 1943, the Navy fired 36,370 anti-aircraft rounds. Only 25% used proximity fuses. But those 25% accounted for 51% of kills. Against the V-1 flying bombs attacking London in mid-1944, the improvement was even more dramatic. British anti-aircraft batteries defending the coast initially destroyed 17% of incoming Vone second. After proximity fuses were deployed, the destruction rate rose to 74%. On the best day, 82%. Without proximity fuses, London would have been systematically destroyed. The technology saved thousands of civilian lives, but the Pentagon refused to authorize use over land. The risk was too great. If a dud fell into German territory, German engineers might recover it, reverse engineer it. Germany had been researching proximity fuses since the 1930s, more than 30 different designs developed or studied. Acoustic fuses triggered by engine sound, electrostatic fuses based on capacitive effects, radio fuses similar to Allied designs. None reached production. German engineers concluded the concept was impossible. The acceleration, forces, and spin rates of artillery shells would destroy any electronic device. They were wrong, but their conclusion meant German intelligence never looked for proximity fuses. Even when German forces captured Allied ammunition, the Battle of the Bulge provided the test. During the offensive, German units overran an American ammunition dump, 20,000 proximity fuses for artillery shells, wooden crates, clearly marked. German soldiers loaded them onto trucks, transported them to rear areas. German ordnance officers examined them, tested a few, declared them to be standard time fuses with unusual markings, stored them in warehouses, never realized what they had captured. The impossible acceleration problem meant proximity fuses could not exist, so German engineers did not see what was right in front of them. Meanwhile, American artillery units used the fuses with devastating effect. Patton's Third Army moved north to relieve Bastogne on the night of December 25th and 26th. Artillery battalions caught a German battalion attempting to cross the Sauer River. Battalion concentration, all guns firing on one target, every shell with a proximity fuse. By actual count, 702 Germans killed, one artillery battalion, one target, 700 casualties in minutes. Patton wrote to the War Department, "The new shell with the funny fuse is devastating. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." The impact went beyond casualties. The psychological effect was profound. German soldiers could not understand how the shells worked. Prisoners of war, when interrogated, repeatedly spoke of the demoralizing effect. Quick, powerful bursts for which there was simply no defense. Artillery that found you wherever you hid. That penetrated any cover. That killed you in your foxhole. One American intelligence report noted German commanders offered rewards for soldiers who found an intact fuse. None were ever recovered in working condition. The self-destruct mechanisms ensured that any fuse that failed to detonate properly destroyed itself. A small charge melted the critical components. Even if Germans found a dud, they recovered only slag, enough to know something was there, not enough to understand how it worked. The airbursts cut communication wires more easily than ground impacts. German units lost contact with headquarters. Forward observers could not call for support. Infantry companies were isolated. Command and control degraded. Tactical coordination became impossible. Some German units experienced what American reports called minor mutinies. Soldiers refusing to leave bunkers during artillery bombardment, not cowardice, rational self-preservation. If there was no way to survive advancing under that fire, why advance? Officers could order movement, but soldiers knew those orders were death sentences. Unit cohesion collapsed, advances stalled, attacks faltered. The German offensive, which had achieved surprise and initial success, ground to a halt, not primarily because of American counterattacks, not because of tactical mistakes, because German forces could not advance under proximity-focused artillery fire, and American artillery was everywhere. By December 24th, the weather cleared. Allied aircraft returned, P-47 Thunderbolts, P-51 Mustangs, RAF Typhoons. They struck German columns with rockets and bombs, supply lines were cut, fuel deliveries stopped, ammunition convoys burned. But the aircraft were temporary. Weather could ground them again. Proximity-focused artillery worked regardless of weather, day or night, clear skies or blizzards. The shells detonated overhead with perfect consistency. German commanders tried to adapt. They ordered units to avoid open ground, move only through forests where tree cover might deflect fragments. But forests offered their own problems. Limited visibility, restricted maneuver, easy to defend. American units used the woods to channel German advances into kill zones, then called artillery. Proximity fuses worked just as well above trees as above open ground. Perhaps better. Fragments that struck branches shattered into smaller pieces. Secondary shrapnel. More wounds per shell. Some German officers suggested moving only at night. Darkness might provide concealment from artillery observers, but proximity fuses did not require observers. Fire based on map coordinates. Fire based on reports of enemy locations. Fire based on calculated positions. The shells found their targets regardless of visibility. December 22nd, 1944. Interrogation Center, Malm, Belgium. Hauptmann Werner Hoffmann sat across from an American intelligence officer, answering questions. Hoffmann commanded a company in the 12th SS Panzer Division. His unit had been caught in the open by American artillery. 23 men killed, 41 wounded. The American officer asked about the artillery. Hoffmann described shells exploding overhead. No impacts on the ground, just airbursts, perfectly timed, every shell. The officer asked if German artillery could achieve similar effects. Hoffmann said yes, with skilled crews and good observation. But these American shells were different. They did not require observation. They detonated automatically, at the same height, every time. How did they work? Hoffmann did not know. No German soldier knew. The technology was completely outside their experience. The officer made notes. Hoffmann's description matched reports from other prisoners. The psychological impact was consistent across all German units. Demoralization, fear, reluctance to advance. Some prisoners spoke of feeling helpless. Artillery had always been dangerous, but soldiers developed tactics to survive it. Dispersal, covered positions, movement during lulls. Those tactics no longer worked. The American artillery found you regardless. Hoffmann said his men called it the invisible killer. You heard the shell coming, then the airburst overhead, then fragments. You could not see the explosion. You could not predict where it would detonate. You just knew it would explode directly above you. One of Hoffmann's sergeants had led a platoon through Soviet artillery barrages on the Eastern Front, Stalingrad, Kursk, the Dnieper. He survived all of that. He told Hoffmann that American artillery was worse. Soviet artillery fired more shells, heavier bombardments, longer duration, but most Soviet shells exploded harmlessly, buried in the ground, detonating too high, wasted rounds. You could survive by staying low, by moving between impacts, by accepting that most shells would miss. American artillery was different. Almost every shell was lethal. The sergeant said, "They do not waste ammunition. Every shell kills. There is no surviving this. We can only avoid being where the shells land, but we cannot attack and avoid artillery simultaneously, Hoffman agreed. His company had been ordered to assault an American position. The approach required crossing 300 meters of open ground. Hoffman had led similar assaults in Normandy. Losses were acceptable if the objective was achieved, but the proximity foe's artillery made the assault impossible. His men reached the halfway point. American artillery opened fire. The first salvo landed among the leading platoon. Airbursts, fragments from above. 12 men down instantly. The survivors went to ground. Second salvo. More airbursts. Precise coverage. 8 more casualties. Third salvo. Fourth. Fifth. The shells walked across Hoffman's entire company. Methodical, efficient, devastating. Within 2 minutes, half his company was dead or wounded. The survivors retreated. Hoffman did not try to stop them. There was no tactical solution. You could not charge through that fire. You could not suppress it. You could only withdraw and report that the objective was unattainable. The American officer asked if Hoffman's unit had any countermeasures. Hoffman said no. How do you counter artillery that requires no observation? That detonates automatically? That finds you regardless of terrain or weather? The Germans had nothing similar. The American officer asked about German artillery doctrine. Hoffman explained the standard approach. Forward observers identify targets, calculate range and bearing, radio coordinates to fire direction centers. Gun crews compute firing solutions, set fuses manually, fire. Observe impacts, adjust, fire again. The process required trained observers, reliable communications, skilled crews, accurate maps. Even with all that, achieving airbursts was difficult. The fuses had to be set precisely. The shells had to detonate at exactly the right moment. Most crews relied on impact fuses because they were reliable. Airbursts were possible but rare. Hoffman said maybe 1 in 10 German. Shells achieved an effective airburst. The rest detonated on impact or failed entirely. But the American shells? Every single one. Perfect airbursts, every time. The only explanation was automatic fuses. Some device that sensed the ground and detonated at the optimum height without manual setting. The technology required electronics, radio equipment, small enough to fit in a shell, rugged enough to survive firing, reliable enough to work every time. Hoffman had never heard of such a device. The interrogation continued. The American officer asked about German morale. Hoffman was honest. Morale was collapsing, not because soldiers lacked courage, because they could not see how to win. The offensive had stalled. American reinforcements were arriving. Allied aircraft controlled the skies. And now American artillery was using weapons German soldiers could not counter. The combination was overwhelming. Hoffman said many of his men believed the war was lost. They fought because they were soldiers, because orders required it, not because they expected victory. The American officer made final notes, thanked Hoffman, had him escorted back to the holding area. The information would be compiled with reports from hundreds of other prisoners. The pattern was clear. Proximity-foes artillery was breaking German offensive capability, not just through casualties, through psychological impact. German soldiers who survived the bombardments were too shaken to continue attacking. Units that maintained tactical cohesion under Soviet artillery broke under American proximity fuses. The weapon was achieving effects far beyond its direct lethality. January 3, 1945. Section T Headquarters. Applied Physics Laboratory. Johns Hopkins University. Silver Spring, Maryland. Dr. Merle Tuve sat in his office reading field reports from Europe. Section T had developed the proximity fuse. Tuve had led the project since 1940, 4.5 years of research, testing, production problems, bureaucratic battles. Now the weapon was proving its worth in the largest battle American forces had ever fought. The reports detailed effectiveness rates, casualty ratios, ammunition consumption figures. The data confirmed what Tuve's team had predicted. Proximity fuzzes increased artillery lethality by factors of 5 to 10 compared to traditional fuses. But the numbers only told part of the story. The psychological impact was equally significant. German prisoners consistently reported demoralization, fear, unit cohesion breakdown. Tuve had not anticipated that. The project goal was technical. Build a fuse that could survive 20,000 Gs of acceleration, make it reliable enough for mass production, ensure it detonated at the optimum height. Those were engineering problems, difficult but solvable. The psychological warfare aspect was an unexpected bonus. When German soldiers could not understand how a weapon worked, they could not develop countermeasures. When every tactical doctrine they knew became obsolete, they lost confidence in their training and leadership. When artillery became inescapable, soldiers refused to advance. Tuve reviewed the development timeline. The concept was old. Gunners had wanted proximity fuses for decades. The challenge was making them work. Early ideas included optical systems. Shine a light, infrared, trigger when reflection reached a certain threshold. But optical systems were fragile, easily damaged, ineffective in smoke, fog, darkness. Ground-triggered systems using radio signals were considered. Capacitive methods similar to metal detectors. Inductive systems. All suffered from the same problems. Pre-war electronics were too large, too fragile, too complex. Vacuum tubes were the size of light bulbs. Circuits required dozens of components. Batteries were heavy and unreliable. Nothing could survive artillery acceleration. The breakthrough came in 1940 when the British Tizard mission shared radar research with American scientists. Miniature vacuum tubes. Radio frequency circuits. The potential for ruggedized electronics. Section T was established in July 1940 under the National Defense Research Committee. Tuve recruited the best physicists and engineers available. The team included men who would later become famous in their fields. James Van Allen, who would discover the radiation belts around Earth. Ralph Baldwin, who would become a leading planetary scientist. Harry Diamond from the National Bureau of Standards. Lloyd Berkner, who developed the separate transmitter-receiver circuit that made the final design possible. The work was extraordinarily difficult. Consider the vacuum tubes. Standard tubes shattered under even moderate acceleration. The glass was too thin, the internal elements too delicate. The filaments snapped. The anodes cracked. Section T needed tubes that could survive 20,000 Gs. Sylvania Electric developed a solution. Thick glass, envelopes, reinforced internal structures, rugged filaments. The tubes were tested by firing them from guns. Most broke. The survivors were analyzed. Improvements were made. More tests. More failures. Eventually, tubes that consistently survived. Production began at Sylvania's plant in Ipswich, Massachusetts. Women assembled the delicate components by hand. Hundreds of women. Tedious work that strained the eyes. The women did not know what they were building. Security was absolute. They were searched entering and leaving the plant. No purses allowed. Even local police and fire departments could not enter the building. By 1945, those women had assembled over 8 million proximity fuzzes. The batteries presented another challenge. The fuse needed electrical power. A battery small enough to fit inside an artillery shell, rugged enough to survive firing, capable of activating instantly under extreme acceleration. Reserve batteries were developed. Glass ampoules containing electrolyte. Firing acceleration shattered the ampoules. The electrolyte mixed with chemicals. The battery activated. Power flowed. The entire process took milliseconds. The safety mechanisms were critical. The fuse could not detonate prematurely. Gun crews handling the ammunition needed to be safe. Ships carrying thousands of shells needed protection against accidental detonation. Multiple safety features were designed in. Mechanical safeties that unlocked only after the shell left the gun barrel. Centrifugal switches that closed only when the shell reached full spin. Time delays that prevented detonation for the first few hundred meters of flight, self-destruct mechanisms that melted critical components if the fuse failed to detonate properly. Testing was exhaustive. Fuses were fired at water targets in Chesapeake Bay, at drone aircraft over proving grounds, in all weather conditions, at all temperatures. Failure rates were tracked. 52% success in early tests. Unacceptable. Improvements were made. Redesigns, new components, better sealing against moisture. By 1943, reliability reached acceptable levels. Not perfect, but good enough for combat. The Navy accepted 50% failure rates if the weapon was still more effective than alternatives. And it was. Far more effective. Production ramped up. 5 companies manufacturing fuses. Over 100 manufacturers producing components. The entire industrial capacity of the United States mobilized to produce a device the size of a milk bottle. The secrecy was unprecedented, second only to the Manhattan Project. The device was never called a proximity fuse in official communications. Code name VT, variable time, elegant misdirection. If German intelligence intercepted communications about VT fuses, they would assume it referred to improved time fuses, which was technically true. The fuse did vary its detonation time, just automatically instead of manually. Personnel working on. The project signed security oaths. Violations meant prison. The consequences were explained clearly. If proximity fuses fell into German hands, they could be used against Allied bombers. The bomber offensive might fail. The invasion of Europe might become impossible. Hundreds of thousands of additional casualties, perhaps losing the war. Everyone understood the stakes. The Pacific Theater used proximity fuses from January 1943 onward. Over water, the risk of German capture was minimal. Dud shells fell into the ocean. Salt water destroyed the electronics. Even if Japanese forces recovered a fuse, they could not easily share it with Germany. The Atlantic crossing was too dangerous. American submarines controlled the sea lanes. But Europe was different. Land combat meant duds could fall into German hands intact. German engineers were skilled. German industry was advanced. If they reverse-engineered the technology, the consequences would be catastrophic. So the Pentagon refused authorization for land use. Navy only. Over water only. The embargo lasted until December 1944. Eisenhower demanded authorization. The Battle of the Bulge was the crisis point. American forces were surrounded. Artillery was the only immediate support available. Without proximity fuses, American positions might be overrun. With them, German attacks could be stopped. Eisenhower's argument was simple. The risk of capture was outweighed by the risk of defeat. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The authorization came through. 200,000 shells shipped to Europe. Codename POSIT. Every artillery battalion received detailed instructions. Fire these only in emergency situations. Recover all duds immediately. Destroy captured ammunition if enemy breakthrough is imminent. Do not allow these fuses to fall into enemy hands under any circumstances. The field reports now crossing Tuve's desk confirmed the decision was correct. German forces had captured 20,000 fuses, but German engineers dismissed them as unusual time fuses. The impossible acceleration problem meant proximity fuses could not exist. So, German ordnance officers never looked closely enough to understand what they had. Meanwhile, American artillery was devastating German formations. Casualty rates 10 times higher than with traditional ammunition. Psychological impact beyond measurement. German units refusing to advance. Attacks stalling. The offensive collapsing. Tuve felt satisfaction mixed with exhaustion. 5 years of work, billions of dollars, thousands of people involved. One of the largest scientific projects in American history. And it worked. Not perfectly. Failure rates were still around 50% in some conditions, but even with 50% success, Proximity fuses were more effective than 100% traditional fuses. The mathematics were undeniable. But Tuve also understood what this meant for future warfare. Proximity fuses changed the calculus of ground combat. Artillery became far more lethal. Advancing under fire became far more costly. Defensive positions became far stronger. Attackers needed overwhelming superiority to overcome dug-in defenders with proximity-focused artillery support. The implications were profound. Wars might become more static. Offensives might become rarer. Casualties might increase dramatically. Or perhaps armies would adapt, develop new tactics, more dispersal, more cover, more indirect approaches, night operations, infiltration instead of frontal assault. The technology would force tactical evolution, just as machine guns had forced tactical changes in World War I. Just as tanks had revolutionized maneuver warfare in World War II, proximity fuses would reshape how ground forces fought. Tuve hoped the war would end soon. Germany was clearly losing. The Soviet Union was advancing from the east. American and British forces were preparing to cross the Rhine. Japan was being strangled by blockade and bombardment. Victory was a matter of time, but he worried about the future. Proximity fuses were just the beginning. What other weapons would emerge from this war? What technologies would the next war bring? The atomic bomb was nearly ready. Tuve knew about the Manhattan Project. Most Section T physicists did. The scientific community was small. People talked, not officially. But everyone knew something enormous was being developed in New Mexico. If atomic bombs worked as predicted, warfare would change completely. Cities could be destroyed in seconds. Entire nations could be eliminated. The scale of destruction would be unimaginable. Tuve returned to the field reports. His job was to ensure proximity fuses continued working. Production had to be maintained. Quality control had to be rigorous. Field problems had to be solved immediately. Artillery crews needed training materials, maintenance procedures, troubleshooting guides. The war was not over. Germany still had fight left. Japan would resist invasion. More proximity fuses would be needed. More lives would be saved by the technology his team developed. That was what mattered now. January 12, 1945. Prisoner of war camp, Luxembourg. Oberst Hans von Luck sat in an interrogation room, answering questions from American intelligence officers. Von Luck commanded a Panzer regiment in the 21st Panzer Division, a professional soldier, North Africa veteran, Normandy veteran, now a prisoner. The American officer asked about artillery. Von Luck described the American bombardments, shells exploding overhead, airbursts, consistent height, every shell. The officer asked if von Luck understood how the fuses worked. Von Luck said he had theories. Some kind of automatic trigger. Radio waves, perhaps. The shell sensed the ground and detonated at the appropriate distance. The officer neither confirmed nor denied. Von Luck continued. Whatever the mechanism, the effect was devastating. German tactical doctrine became obsolete. Everything German soldiers had learned about surviving artillery bombardment no longer applied. Trenches were death traps instead of protection. Forest cover was useless. Buildings offered no safety. The only option was deep bunkers with reinforced concrete overhead. But you could not fight from deep bunkers. You could not maneuver. You could not attack. Defensive warfare was possible. Offensive warfare was not. Von Luck said the proximity fuses, whatever they were, fundamentally changed ground combat. He compared it to the introduction of machine guns in World War I. At first, armies tried to attack machine gun positions using 19th century tactics. Mass infantry charges, close formations, frontal assaults. The results were catastrophic. Hundreds of thousands of casualties. Eventually, armies adapted. New tactics, infiltration, combined arms, artillery support, tank support. But the adaptation took years. Von Luck believed proximity fuses would require similar adaptation. German forces had not had time to develop countermeasures. The technology appeared in December 1944. By January 1945, Germany was retreating. There was no time to analyze the weapon, no time to develop new tactics, no time to train soldiers in different approaches. The American officer asked what countermeasures might work. Von Luck thought about it. More dispersal would help. Spread units over wider areas, reduce casualties per shell, but dispersal weakened attack strength. You needed concentration to achieve breakthrough. Concentration made you vulnerable to proximity-focused artillery. The contradiction was unsolvable. Better armor might help. Overhead protection on vehicles, reinforced roofs. But that added weight. Vehicles became slower, less maneuverable, easier targets for anti-tank weapons. Another contradiction. Night operations might reduce casualties. Darkness made artillery observation harder. But proximity fuzzes did not require observation. They worked day or night. Weather was no help either. Fog, snow, rain, none of it mattered. The shells found you regardless. Von Luck concluded that no countermeasure was effective except avoiding areas under American artillery coverage, which meant avoiding combat entirely, not a viable military strategy. The officer asked about German artillery. Could German forces develop similar technology? Von Luck said theoretically yes. Germany had excellent engineers, advanced research programs, but Germany lacked industrial capacity. Factories were being bombed daily. Raw materials were scarce. Transportation networks were destroyed. Even if German engineers designed a proximity fuse, production would be impossible, and it would be too late. The war was ending. Von Luck could see that clearly. The Battle of the Bulge was Germany's last offensive, the last strategic reserve, the last chance to change the war's trajectory. It failed. German forces were back to their starting positions. American and British forces were preparing to cross the Rhine. Soviet forces were advancing toward Berlin. Germany had no more reserves, no more fuel, no more aircraft, no more hope. Von Luck said this as fact, not emotion. A professional military assessment from a professional soldier. The officer made notes, asked a few more questions. Thanked Von Luck, had him escorted back to the compound. Later, Von Luck would be transferred to a camp in England. He would spend the next year as a prisoner, then release, return to Germany, a long post-war life. He would write memoirs, give interviews, speak at military colleges. Always, he would mention the proximity-focused artillery, the weapon that rendered German tactical doctrine obsolete, the technology Germany could not match, one of many factors that led to defeat, but a significant factor, maybe not decisive by itself, but combined with Allied air superiority, Soviet numerical advantage, American industrial capacity, British intelligence, German strategic mistakes, Hitler's interference, fuel shortages, manpower exhaustion. The cumulative weight was overwhelming. Proximity fuses were part of that weight. Small devices, milk bottle-sized. But they changed how ground forces fought, made artillery far more lethal, made offensive operations far more costly, broke German morale in the Battle of the Bulge, February 9, 1945. War Department, Washington, D.C. General Levin Campbell, Chief of Army Ordnance, read Patton's letter again. The funny fuse won the Battle of the Bulge for us. I am glad that you all thought of it first. High praise from Patton, who was not known for praising anyone. Campbell understood what Patton meant. The Battle of the Bulge was decided by many factors: American resilience, rapid reinforcement, Allied air power once weather cleared, German fuel shortages, strategic mistakes by Hitler. But proximity-fuzzed artillery was critical. It stopped German advances cold, prevented breakthroughs, inflicted casualties that German forces could not replace, broke unit cohesion, demoralized soldiers. Without proximity fuses, the battle would have lasted longer. American casualties would have been higher. German forces might have reached the Meuse River, might have captured critical supply depots, might have prolonged the war by months. Campbell looked at production figures. 22 million fuses manufactured by the end of the war. Over 100 manufacturers involved. Billions of dollars invested. The largest electronics manufacturing project in history until that point. All to produce a device that fit inside an artillery shell. The return on investment was undeniable. Proximity fuses were used in multiple theaters. Pacific naval warfare against Japanese aircraft. European air defense against VUN flying bombs. Ground. Combat in the Battle of the Bulge and subsequent operations. Each application saved lives, shortened campaigns, increased effectiveness. The Navy credited proximity fuses with enabling the advance across the Pacific. Without them, kamikaze attacks would have inflicted far higher casualties, possibly enough to force changes in strategy. The British credited proximity fuses with saving London from V1 destruction. Without them, the flying bomb campaign would have devastated the city, killed tens of thousands, possibly forced evacuation of the government. The army credited proximity fuses with breaking the Battle of the Bulge. Without them, German forces would have advanced further, caused more casualties, possibly reached strategic objectives. Campbell authorized continued production. The war was not over. Germany would fall soon, but Japan remained. Invasion of the home islands would require massive artillery support. Proximity fuses would be essential. Casualty estimates for invading Japan were staggering. Hundreds of thousands of American casualties expected. Millions of Japanese casualties. Anything that reduced those numbers was worth producing. Proximity fuses would save American lives. That justified the cost. But Campbell also received reports from intelligence officers about German research. German engineers had been developing proximity fuses since the 1930s. Multiple designs: acoustic fuses, electrostatic fuses, radio fuses. None reached production. But the research existed. If Germany had succeeded 6 months earlier, Allied bomber losses would have increased dramatically. The strategic bombing campaign might have failed. Air superiority might have been lost. Invasion of Europe might have been impossible. The timing was critical. America developed proximity fuses first, deployed them first, maintained secrecy long enough. If Germany had succeeded first, the war might have turned out very differently. Campbell thought about that often. How close the margins were, how much depended on timing, on individual decisions, on breakthroughs happening in the right order at the right time. The proximity fuse was one of many technologies that gave the Allies advantage. Radar, sonar, code breaking, penicillin, DDT, synthetic rubber, mass production techniques. Each contributed to victory. Each shortened the war. Each saved lives. But proximity fuses were unique. They were the first smart weapons, the first munitions that adjusted their own behavior based on the tactical situation, the first artillery shells that did not require manual fuse setting, the first automatic weapons that used electronics to increase lethality. They pointed toward the future. Guided missiles would follow the same principle: sense the target, adjust the trajectory, detonate at the optimum moment. Smart bombs would use similar technology: television guidance, laser guidance, eventually GPS guidance, all descendants of the proximity fuse, all based on the same concept: give the weapon enough intelligence to make its own decisions. Campbell approved additional funding for post-war research. The war would end, but weapons development would continue. The next war would require new technologies: better radar, better guidance systems, better automation. America needed to maintain the technological edge. That edge had won this war. It would be needed for whatever came next. March 7th, 1945. Remagen Bridge, Germany. American forces crossed the Rhine. German resistance was collapsing. The war in Europe had less than 2 months left. Between the Battle of the Bulge and the Rhine crossing, American artillery fired hundreds of thousands of proximity-fused shells. German formations were caught in the open, caught retreating. caught trying to establish defensive lines. The airbursts were devastating. No place to hide, no way to avoid the fragments. Casualties mounted until German units simply dissolved. Men surrendered, deserted, fled. Anything to escape the artillery. Allied anti-aircraft batteries using proximity fuses shot down over 1,000 German aircraft in the same period. The Luftwaffe, already depleted, lost planes it could not replace, pilots it could not replace. The few remaining aircraft were grounded for lack of fuel. The German war machine was broken, not by one weapon, not by one battle, but by cumulative attrition. Every advantage the Allies possessed, every disadvantage Germany suffered, all combining into overwhelming pressure. Proximity fuzzes were part of that pressure, not the whole story, but a significant part. They increased artillery effectiveness by factors of 5 to 10. They broke German morale. They prevented German offensives. They shortened the war. How much shorter? Impossible to calculate precisely, but analysts estimated weeks at minimum, possibly months. Every week the war ended sooner meant thousands of lives saved. Allied lives, civilian lives, even German lives. The destruction of Germany was terrible, but it would have been worse if the war continued. More cities bombed, more civilians killed, more soldiers dead in pointless last stands. Proximity fuses helped end it faster. Historians would later debate whether the proximity fuse was as important as radar or code breaking, whether it deserved to be ranked with the atomic bomb as a decisive weapon. The arguments would continue for decades, but the soldiers who fought in the Battle of the Bulge had no doubt. They knew what proximity-fused artillery did. They saw German attacks stop. They watched enemy formations disintegrate. They survived because the technology worked. Patton said it clearly. The funny fuse won the Battle of the Bulge for us. Maybe an overstatement, but not by much. May 8th, 1945. Victory in Europe Day. Germany surrendered unconditionally. The war in Europe was over. But the war against Japan continued. Proximity fuzzes were shipped to the Pacific in massive quantities. Artillery battalions preparing for the invasion of Japan received priority deliveries. The invasion was scheduled for November. Operation Downfall. 2 phases. Olympic and Coronet. Assault the home islands. Fight through fanatical resistance. Casualties estimated in the hundreds of thousands. Proximity-fused artillery would be essential. Break Japanese defensive positions, suppress counterattacks, provide fire support for advancing infantry. The logistics were planned in detail. Millions of shells, hundreds of thousands with proximity fuses, stockpiled on Pacific islands, ready for the invasion. But the invasion never happened. August 6th, 1945. Atomic bomb dropped on Hiroshima. August 9th. Atomic bomb dropped on Nagasaki. August 15th. Japan surrendered. The war was over. The invasion was cancelled. The proximity-fused ammunition stockpiled for Operation Downfall was never used. The shells were eventually fired in training exercises. Dismantled. Stored. The technology was declassified gradually over the following years. First, the basic principle, radio detection, automatic detonation. Then, the engineering details, ruggedized vacuum tubes, reserve batteries, safety mechanisms. By the 1950s, proximity fuses were standard equipment in all American artillery. By the 1960s, every NATO nation used them. By the 1970s, even non-aligned nations had developed similar technology. The principle spread. Guided missiles used proximity fuses. Air-to-air missiles, surface-to-air missiles, anti-ship missiles. Smart bombs used proximity sensors. Laser-guided munitions, GPS-guided munitions. The technology evolved, but the core concept remained. Sense the target. Detonate at the optimum moment. Maximize lethality. Dr. Merle Tuve retired from the Applied Physics Laboratory in 1946. He became director of the Carnegie Institution's Department of Terrestrial Magnetism. He continued research in geophysics and radio astronomy. He received numerous awards for his wartime work: the Presidential Medal for Merit, the King's Medal for Service in the Cause of Freedom from Britain, honorary degrees from multiple universities. But he rarely spoke publicly about the proximity fuse. The work was classified for years. Even after declassification, he remained modest. The proximity fuse was a team effort. Hundreds of scientists, thousands of engineers, millions of factory workers. He led Section T. But the success belonged to everyone involved. Tuve died in 1982. His obituaries mentioned the proximity fuse prominently. The weapon that changed warfare. The smart weapon before smart weapons existed. The technology that helped win World War II. The German perspective came slowly. In the immediate post-war period, German officers were reluctant to discuss advanced Allied technologies. It was painful to acknowledge how comprehensively Germany had been outproduced and out-innovated. But gradually, memoirs appeared. Technical analyses were written. The truth became clear. Germany never came close to developing a working proximity fuse. The acceleration problem defeated every design. German engineers who examined captured ammunition after the war were astonished. Miniature vacuum tubes that could survive 20,000 Gs, circuits simple enough for mass production, batteries that activated under extreme shock. It was engineering brilliance they had not matched. Field Marshal Model said it clearly in a post-war interview. "We knew American industry was powerful. We did not know American engineering was so advanced." Generaloberst Heinz Guderian, when asked about proximity fuses, said, "If Germany had possessed such weapons, we might have held the Allies at the Rhine for months, but we did not possess them, we could not produce them, and by the time we understood what the Americans had, it was too late to develop countermeasures." The Battle of the Bulge veterans carried memories of proximity-fused artillery for the rest of their lives. American veterans remembered how the new ammunition stopped German attacks, how positions that seemed impossible to hold were successfully defended, how the tide turned in late December when the weather cleared and artillery could fire without restriction. German veterans remembered the terror of shells exploding overhead, the feeling of helplessness, the knowledge that no tactical skill would save you from invisible weapons, the abandonment of offensive operations because advancing under that fire was suicide. Some German veterans, in their later years, said the proximity fuses were the moment they knew Germany had lost, not because of the casualties the fuses inflicted, because of what the technology represented. An enemy that could develop, produce, and deploy millions of miniature radar sets inside artillery shells was an enemy that could not be defeated. The industrial capacity was too great. The engineering capability was too advanced. The resource advantage was too overwhelming. One German panzer commander, interviewed in the 1980s, put it simply, "When I saw American soldiers eating from individual packaged meals with chocolate and cigarettes, I thought we might lose. When I experienced shells exploding exactly overhead every single time, regardless of conditions, I knew we had lost." You cannot defeat an enemy who treats complex electronics as disposable ammunition. The mathematics supported that assessment. Germany produced approximately 120,000 military aircraft during the war. America produced 300,000. Germany produced 46,000 tanks. America produced 63,000. But more importantly, American tanks were simpler, more reliable, easier to maintain. American aircraft used standardized parts. American logistics kept everything supplied. The proximity fuse was an extension of that philosophy. Solve problems with engineering and production. Make sophisticated technology reliable enough for mass use. Deploy it in quantities that overwhelm the enemy. 22 million proximity fuses produced. Each one a tiny radar set. Each one capable of functioning reliably under extreme conditions. Each one representing industrial capacity Germany never possessed. The German soldiers at the Battle of the Bulge opened American K rations and saw industrial abundance. They experienced proximity-fused artillery and saw technological superiority. Both pointed to the same conclusion. America possessed resources Germany could not match. The rations were evidence. The proximity fuses were proof. When artillery shells became smart weapons, warfare changed. Not immediately, not obviously, but fundamentally. The proximity fuse was the first weapon that sensed its environment and adjusted its own behavior. It was the ancestor of every guided missile, every smart bomb, every autonomous weapon system, every device that makes its own tactical decisions. The principle was simple. Give weapons enough intelligence to improve their effectiveness, reduce the human workload, increase lethality, automate what can be automated. World War II ended with proximity fuses demonstrating the concept. The Cold War refined it. Modern warfare depends on it. Today's artillery shells have GPS guidance. Today's missiles have terminal seekers. Today's bombs have laser designators, all descendants of the proximity fuse, all based on the same idea: make weapons smart enough to hit their targets without constant human control. The German soldiers in December 1944 faced the future. They did not understand it. They had no defense against it. And they learned, in the frozen forests of Belgium, that some technological advantages cannot be overcome by courage or skill or tactical brilliance. Sometimes the side with better engineering simply wins. Thank you for watching. For more detailed, historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.